Use the data below to find the correlation coefficient R for the height-weight relationship for supermodels. So we have the summary values here, summation of x squared, dot, 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 so on and so forth, right? For the different heights and weights. All right, so let's talk about what we're asked to find here. We want to find the correlation coefficient R. So we're going to use these values that are provided to help us do that. In order to do that, we're going to need to fill in the following formula for R. Remember that R is equal to a ratio here. It has the summation, or the sum of squares, pardon me, of xy above the square root of the sum of squares for xx times the sum of squares for yy. So it's our goal to get these sum of square values so we can enter them into our formula. So we'll start with sum of square xx, then we'll do sum of square xy, and then we'll do sum of square yy. All right, let's fill in the formulas then for sum of square xx. It's the summation of x squared minus the summation of x quantity squared all over n, the number of ordered pairs we have. This formula will be the summation of xy minus the summation of x times the summation of y all over n. And this last one is the summation of y squared minus the summation of y quantity squared all over n. Okay, so let's fill in what we know from the problem. The summation of x squared is given as 44,399.5 minus the summation of x. The summation of x is 632. Quantity squared divided by n, how many data values we had to start with. That's 1, 2, 3, 4, 5, 6, 7, 8, 9 different ordered pairs. So 9 is our n. Remember, n represents the number of ordered pairs. We'll come and work that out in a second. And we have the summation, or the sum of squares, pardon me, of xy. So we need the summation of xy first. That's going to give us 76,546 minus the summation of x, which is 632, times the summation of y. The summation of y is 1,089. And all of that, again, will be over the number 9. Okay, and then we have the summation of y squared. That's 132,223 minus the summation of y. The summation of y is 1089 quantity squared over 9. Okay, now let's go ahead and work these out with our calculator and fill in their values. So we'll start with the top one, summation of x. It's 44,399.5 minus 632 squared divided by 9. When you're done, you get the answer 19.05 repeating. All right, then for the sum of square xy, we have 76,546 minus 632 times 1089 divided by 9. We get the answer 74. And then we'll have 132,223 minus 1089 squared divided by 9. All right, when we're done, we get the answer 454. Okay, so those are nice values there. Most of them are round, and the other one that continues at least repeats. So when we enter them into our formula, it should be nice and easy to get the solution here. Starting with SSXY, that value is 74. Then the sum of square xx, that's 19.05 repeating, times SSYY, which is 454. So 454 after that. All right, let's plug that in our calculator, see what R turns out to be. So we'll have 74 divided by the square root of, in this case it would be 19.055555 times 454. Close the parenthesis for the square root, hit enter, and we get the answer 0.796. Okay, so that's rounding it, so it's approximately 0.796. That's a pretty strong R. It's close to 0.8. At that point, we'd say there's a reasonably strong linear correlation between the height and weight of supermodels, which is probably something we expect to be true. Generally speaking, a person who's taller weighs more, so this is conveying a positive relationship, which means that the data values move in the same direction. That means as a person gets taller, their weight increases. So this is indicated by the positive R, and the fact that it's almost 0.8 means it's a pretty strong linear relationship.